Up next, we have John Hoot, who's going to be talking about modeling binary stars using Gaia Parallax data.
That's a good. Okay, so historically, people were interested in binary stars primarily as ways to measure distance within our galaxy. If you could determine the temperature and get radial velocity data such that you could determine the mass of the star, you could then determine the distance to that star. Now, after Gaia, that technique is probably done. But in the fact that it is, made me think about, well, let's turn the equation around and make the unknown, okay, the radial velocity, and use Gaia and photometric modeling of binary stars. And as a result, you can then produce models very easily with just photometric data. So I went around and thought about it and read about it. And here's where I am on it. Give me a hand here. Okay, so here's the cookbook. Of course, the way you do this is you photometrically analyze the star, and you end up with a light curve. Right? And then you plug that into your favorite modeling software. And, you know, Wilson Davini or whatever it is, Binary Maker. And you model the star as best you can using multi-band photometry and its effective temperatures, and you fit it till you get something that looks like it might make some sense. At which point, what you'll have is you'll know what the mass ratio is between your two stars, but you don't know what their absolute mass is. So the next step here is to note the mass ratio of your binaries, and that comes out of your software typically. And then you go to Gaia and you look up its parallax data. And this is a quick look. You go to the Vizier and you take the advanced menu and you say, I'm interested in Gaia data, and you put in your star's name and or coordinates. And it drags up the Gaia catalogs. You pick the one with parallax in it, and it reads you out a parallax. Right? That's in milliarcseconds, and it gives you some error bars. And of course, the inverse of the parallax is how many parsecs away that thing is. So now you know the distance to the object, and you know its apparent magnitude taken as if it's a single source. Right? And so you compute the absolute luminosity of the pair. And that comes from these formulas, and there's no test at the end here. But basically, absolute magnitude is defined as the brightness of your source if it was sitting 10 parsecs away from you. Okay? And you can do that for the aggregate pair. And the next step here then is to find, taken as a pair, the absolute luminosity of your system. Now, my first cut at this, I wanted to express this in units that didn't confuse the heck out of me. And, you know, it's solar masses and solar luminosity. So you don't have to work with the ergs and so forth to make this thing happen. Now, I initially used V magnitudes, right? Because the solar V magnitude is well known, but what you really want to use is the bolometric magnitude. But if your star is, you know, in G or F and summa K, you know, the bolometric correction is pretty damn small. So if it's in that color range, go ahead and use the V magnitude of the sun. Otherwise, you're going to have to do the bolometric correction. And so this is the bolometric correction, and it comes out of the literature. So you basically can take your V magnitude, and you can put this adjustment to either your apparent or your computed absolute magnitude, and end up with a bolometrically corrected. What bolometric magnitude means is basically it's the black body from DC to gamma rays, the integration of the whole thing. Well, of course, nobody's scope covers that, so that's what you do. And for bluer sources, that's the whole Megillah there. So it shows you how you can correct your bolometric magnitudes. Now comes the fun part, solving the equation. And we do that by making the initial assumption that each star's luminosity is proportional to the luminosity of the components are proportional to the mass, which is dead wrong, okay? But it's a starting place for an algorithm that's going to iterate and converge until we get the masses to make some sense. Did I just know? Okay. So here's how you basically compute the total luminosity of the system, either magnitude. So that'll give you the sum of the luminosities. And then you recalculate and keep adjusting the luminosities of the primaries and the secondaries until the masses make sense. And this is and you use the mass luminosity ratio with a relation. It's not a function. It's a piecewise continuous function, but not necessarily it's pieced together, it's close to monotonic. And this is the forward one where you take, and you know the masses, and you generate the luminosities. And this is the inverse relation where you take the luminosities and convert the masses. And so the heart of the algorithm here is a loop. And what we do basically is we make that stupid assumption that the mass and luminosities are proportional and assign them appropriately. But then we look at, we calculate, there are two functions, there's mass to luminosity, luminosity to mass. And we iterate through, and each time we look at the masses, okay, and we take the more massive star and we add our error to it. And as a result of that, eventually it converges on two masses that have the right ratio and whose luminosity sums match up the absolute magnitude that we've calculated. And boom, we're done. And the code that's there is actually in the book, but I've of course been tweaking it, adding things like bolometric correction and interstellar reddening, which is the other bugaboo in this thing, because as you look through more of the interstellar medium, the apparent luminosities you get biased toward the red side of things. But Gaia comes in to help you do that too, and I'm working through that. There's a mechanism, I believe, that I'm working on, wherein you basically look in an area around your target for things that are in similar distance, okay, and you look at the Gaia magnitudes and their colors, and you can get a reddening correction. Typically, if you're in near the very galactic disk, you can get as much as 2 magnitudes of reddening, and as you move out of the disk, it becomes less and less important about what you do. And so, sanity check, I took a couple of stars. I've been looking at a lot of stars for a while, and I looked at them eclipsing binaries, and I put them into, I use Nightfall because I happen to find its interface is a lot friendlier than Wilson Divinity. But, and you see the fit. Now this isn't a very great fit right at maxima, but that's more probably my data than the model. And it spits out the numbers for you and gives you a total mass of the system, among other things, which is what this particular modeling program wants. And then it'll compute the individual masses for you and we've already got the luminosities done. And here's what it models, as the light curve indicates. It's a tip-hatched binary system, and we can now actually calculate the radial velocities of the system. And if you go and then look at the proper motion, the radial component from Gaia observations, you'd want to add that to that if you wanted absolute velocities in the system. And sanity check, you plot it on the HR curve, and surprise, surprise, it lies pretty much in the main sequence. We have a cooler red star paired with still another dwarf or sub-dwarf there. And so your basic detached binary pair, but it makes astrophysical sense that they're in that place. And here's now an over-contact system where there's stuff going on. And here we've got a pretty good fit. The residuals are down below there. And they range at a high of 0.16 mag, which is, and these are in units of flux. So take that in a log sense if you want to end up with what we're doing in terms of magnitudes. And there's the model you end up with this solution, and the temperature is reflected in the graphs. And again, you get the radial velocity curves. You plot this one, somewhat similar to the other one. And yeah, so far we're looking like we're in a real place. Now we've got a system that actually goes through a near total eclipse, which helps you figure out what the temperature is on one of the stars pretty easily as a starting point in the model, and that's a bonus. And we went through the same process and ended up with a pretty reasonable model. And we come up with another one of these bowling pins and the mass calculation from the temperatures. And we're fitting to a fraction of a percent here of the magnitude. And here comes, and now we get, and this is IT Herc. And this is where you do a head scratch, okay? Because that's the plot, right? And we've got the smaller star. This is the modeling program that this uses, assigns the primary and secondary with no respect to which is the larger star. So that's the caveat in reading some of this. But what we've got here is it's not a white dwarf. It looks to me like we've got a common envelope here. It looks like it's taken a subdwarf and merged it. It in fact looks like it's starting to move off the main sequence. I don't know if the laser works here. Okay. See right up there, it's just starting to move off the main sequence. Its envelope has expanded. It's eaten its neighbor. They're a common envelope. And so it gives off a temperature indicative of the primary, but in fact it started life as something much smaller. I could be totally off the wall, but that's the best I could come up with based on that. But this is an opportunity to start doing some astrophysics and just look at interesting binaries and learn more about them and put them in a real context as to where they belong in the HR diagram and think about how they have evolved. So, as I said, the next steps, I'm incorporating the bolometric corrections and effective temperature to the system to be done automatically. Right now, you have to sit there and do some fiddling and some math with your models, and depending on which filters you use, you have to use different formulas and tables to determine the effective temperatures of your system. So we're wrapping it all in a GUI, and I'm working on deriving that line of sight readily, so you don't have to sort of look at the galactic latitude and put your finger in the wind and pick your interstellar reddening term. So that's it. That's what's been keeping me off the streets for a couple of weeks. If you have questions, I'm good.
Questions?
It's good to hear you and good to hear you again. Every year I was just telling somebody that, who's John Hoot? And I said, well, every couple of years he comes in and he gives a talk. You never know what the heck it's going to be about. It's always a tremendous insight, whatever you do. Sometimes you pick stuff that looks simple-minded, but somehow when you get finished with it, it's no longer simple-minded. It's got tremendous insight into what's going on in the sky. So now after that, that's supposed to be a compliment.
That's the sugar. Where's the salt?
Okay, here comes the question. I, of course, have my favorite binary star. Can I send that to you and have you model it?
Glad to.
Okay, next question.
I'm also working on a similar thing for pulsating variable stars, and I'm going to actually try and create motion models of pulsating, at least radially pulsating variables based on the same sorts of calculations and techniques with Gaia data. All those old galactic standard candles now just become interesting targets.
Right, we have a two-parter from Joyce Music Online. First one is, could you say more about the contained star in the HR diagram that is below the main sequence but too luminous to be a white dwarf?
Okay. The only explanation, well, the best explanation, there are two possible explanations that are highly probable. One is that there's something wrong with my algorithm, okay, or my data. Okay, it's just flat wrong, you know. And with binary star modeling, you can find weird models that fit. Okay, it's not like there's a right solution. You put different combinations of parameters, temperatures, masses, distance, inclination, and so forth. There are a lot of handles to adjust, and I haven't even started talking about accretion curve disks and things like that. And so I may have just blown this one. That's one possibility. Right? But the other one that I think makes most astrophysical sense within my limited knowledge is that, all right, you had a star that expanded because of the main sequence, and that means that its diameter has increased. Now, its effective temperature, depending on what it's burning, whatever, but it's getting larger, all right? And that envelope, it had a detached companion, but it's swollen up, and they're tidally locked, and at that point is when its outer layer starts to envelop this other star, when they both fill their Roche loads, you get a mixing of the atmospheres of the stars, and they tend towards an equilibrium, which means that this really cool red subdwarf, all right, that just got eaten, all right, now looks like, from a thermal standpoint, a much warmer star, and larger because it's got this envelope that it shares now with its primary. So that's the explanation that I present here.
The second part of the two-parter was also, what language do you program in and how do you make your beautiful graphics?
Okay. I steal the beautiful graphics from the internet for the HR diagrams, and I actually just use for quick and dirty PowerPoint, because then I can draw circles and lines and arrows on them and put things there. The star models are an output of that Nightfall program, and it's written by a German guy, and if you email me, I'll send you a link to where you want this, where you can pick up a copy of the software. Caveat, it runs under Linux, and it uses pgplot, and if you aren't comfortable with some of that stuff, check my paper from, what, 2-3 years ago, and it turns out I will send you, if you send me a blank SD card, a complete Linux environment that runs on a virtual machine that has all this stuff pre-installed.
We have a question back
John, I'm making the problem much more complicated. Does this only work with binary star systems? Can it work with triple
It can, okay, the solution space gets much more complicated. You move basically from a one-dimensional solution space to a two-dimensional solution space with more possible solutions. But determining that you have three components would present an interesting light curve in and of itself. And in terms of solving it, I don't think there's an existing code that I know of for modeling triples. And depending on how close together the three stars are, you might attack it by treating the two closer stars as a single star in your initial solution, and then go to the other two and solve them, and then again work this whole magic backwards as if you're working on two different star systems, and each one is you have a subset solution, and then the total solution that treats the subset as a single object. That's how I might try and skin that cat.
Any more questions? All right, thank
Thank
you,
you.
John. Oh,
I have one. I'm going to betray my ignorance of astrophysics. The idea makes perfect sense to me, and I love it, that you get a relative mass ratio from the light curve solution, and you need more data to use Gaia distance and mass luminosity relationship. Doesn't the mass luminosity relationship inherently assume their main sequence dwarfs? There's another curve for subgiants.
No, that's the multiple discontinuities here. Let me go back here. You can see that there's luminosity ranges. We're talking at the bottom here, okay? Here's where giants live. Here's where dwarf lives. Here's where we live. Here's where the other guys are, okay? So that's why it's a piecewise relation. It's not a function. It's a relation in a series of relations, and it's been empirically determined by lots of people making very good measurements, and I stand on their shoulders.
So you could actually end up on the subgiant branch.
The things you're looking for, apparent magnitude, effective bolometric temperature, okay, and distance. The recipe starts with those three ingredients, and you cook them up, and you come up with an answer.
Okay, makes sense. Thank you, sir.